at my door. The sound of silence, I can't take anymore. Nobody
Test, test. Okay. Hey, folks, we're going to go ahead and get started. If you guys don't mind taking your seats. Thanks. Hey, folks in the back, we're going to go ahead and get started. All right. All right. Cool. Okay. Thanks, everyone. Thanks, everyone, for coming and making your way out here. So I really appreciate this. Let me give a. My name is Danny. I am the engineering manager that's supporting the RocksDB team. So I'll be kind of emceeing the event today. And so it's really exciting to be able to see people across the industry, across all the companies come out and attend our first post-COVID meetup event. So my understanding was that this used to be a pretty regular thing, but we had to stop for obvious reasons. So, given what's going on today, it's exciting to see that we're actually going to start this back up and get people together and have conversation and socialize and learn a little more about what's going on with RocksDB. So before we actually get started with the talks, though, I wanted to just go over a couple of meetups logistics. So first, I think everyone saw the mini kitchen, and it may not be obvious where the bathrooms are, but they're actually behind the fridge over there. So feel free to go over there and obviously use what you need to use. You do need to be escorted by security at all times, so feel free to use the restroom, but don't go wandering around the buildings because security will not be happy about that. So, so please be mindful of that. The other one is that we want to make sure that we have time to get through the presentations, so we're not going to take questions during the presentations. If we have some time at the end of each presentation, there is a mic set up in the middle there. Feel free to go back there and be able to ask your questions. I will be keeping time and making sure that we end and respect each speaker's time. So if there's no questions, if we actually don't have time for questions because the presentation took the whole time, that's okay. Please find the speaker afterwards and ask your questions. And I think their people's contact info should also be in their slides. Finally, the last thing is I will be sending out a survey after. So please be on the lookout for that because we do want feedback on how can we improve this event going forward. This is the first time we're actually also doing a hybrid event. So there's over 100 people that should be on the Zoom call that is also going. So there are people watching from there. So yeah. And finally, just a little anecdote about myself. I actually attended a RocksDB meetup 8 years ago when I was working on storage infrastructure at another company. So I remember it was just an amazing technology that I was really excited to learn about here. And so for me, it's a real special honor to be here organizing one of these events, working on RocksDB. I think it's an amazing technology, being able to support the team here and then having people here to share that excitement with. So again, thank you for coming, and we're really excited to have you. So with that, actually, one last slide. This is the meetup agenda. So just to let you guys know, hopefully we're on time, but we'll have Pliops present on XDP-Rocks right after this, and then we'll try to aim to end around 6:30. We'll have some time to have pizza and just enjoy spending some time with each other. There is also some swag in the back, so if you guys haven't gotten it yet, please go ahead and go back there and grab it when there's a break. So there is going to be a break at 4:55 after the first two talks, and so we'll go from there. So is Ed here? Yep, all yours. Test, test. This is to go forward. Oh, you can see the slides right here. Ed. The slides are right here.
Hi everyone, can you hear me? So yeah, my name is Edward. People usually call me Eddie. I'm VP Technology for Pliops, and we're going to speak about hardware acceleration for RocksDB today. So let's just get started. So I guess that more or less every single one in this room knows that trying to optimize the space around key value storage engine is quite a hassle, as we try to meet many different requirements and make the best use of the resources, both of the storage, the CPU, and the RAM, which gets us trapped in a lot of trade-offs that we solve in this or that way. So RocksDB is an amazing product, no doubt about that, very rich API, but still I'm sure that everyone in this room knows the inherent limitations or trade-offs that make it a bit of headache to use the system's resources. So just to name a few, the classical ones are the write amplification, the read amplification, and the space amplification. We actually cannot use to make the best of all the write and read bandwidth, and we're using more space than we could have, and we're also burning CPU. So actually, a lot of system resources get used in some optimal ways when we run RocksDB, and naturally, it's a very hot topic in the research space, and people keep asking themselves if they can do better. So one approach, which is accidentally adopted by Pliops, is trying to think of a data acceleration technology that is sibling to other technologies like GPUs, DPUs, TPUs, Nitro, etc., with the domain-specific processor plus a software development kit that would serve it. A processor that would approach the storage space as inherently a collection of keys and values rather than just a collection of blocks, so that the key value storage engine trade-offs would be addressed as part of the architecture and not as an afterthought. So such a device would offload the inherent storage access bottlenecks like search, indexing, compression, garbage collection, etc. And maybe as a bonus, it would provide some vital data protection functionality as resilience to storage media and power failures. So those of you that would like to approach us during the break, we can show you a sample of our card, which we've designed, something that we call an extreme data processor, and an XDP. It's a normal standard PCIe card that sticks into the server just next to your storage. We don't do anything about the drives. We just make them work faster. So this just a few we know that it's a software crowd, so we won't be getting into too much details about the hardware. But basically, it's an FPGA device, and the ASIC is upcoming very soon. The ASIC is supporting up to 8 Gen 5 SSD drives, and we have a lot of performance goodies built into it. So on the right side, we manage the storage space on the SSD directly, and we take over all low-level functions like the garbage collection. On the read side, our main innovation is a super compressed index that has a very low memory footprint and can fit into DRAM, so that we can actually address tens of billions of values from one host. On the capacity side, we also offer compression functions like LZ4 and ZSTD. And a nice part for this architecture that comes in handy in many applications is protection, because we can actually implement RAID 5 functions at near zero impact on the application performance. So the reason I've been telling you about all that is that this technology is inherently tied to our offering, which is called XDP-Rocks, which is an accelerated key value storage engine. So actually, why do we need to build a product like XDP-Rocks? The reason is very simple. The reason is that RocksDB is an API that is closest to the standard in this industry, and the very broad base of applications and services are built on top of it. So we cannot ignore this fact. We cannot ignore the fact that a small set of hardware APIs, however fast, cannot cut it. Okay, so that's why we have a two-layered offering. The applications that really need very low-level things just on top of the hardware can use a very crude key-value API. But for the more sophisticated applications that are the majority, we actually provide the full support of the RocksDB API. It's it's drop-in compatibility. You basically just recompile your application with the same API and get the core native XDP performance with that. Implementation in a nutshell: we are based on RocksDB. We're in sync with a pretty new version, 7.0, but there is a very extensive rework of the internals to make it work with our hardware. So some of our trade secrets. Actually, we've already published part of them in the academic conferences, and we'll be publishing more. So one of the principles behind our design is key value separation. So we actually separate the keys from the values. We store the values in our core key value store, which takes out most of the compaction overhead. A lot less bytes need to be moved around. So there are multiple other implementations of key value separation that existed before us, but actually they have different drawbacks. We can talk about them during the break as well, including the scalability of how much of the index can actually be stored in the memory. But the bottom line is that with our implementation, we take out the write amplification overhead. So on the read side, though, things get even more interesting as we employ an optimization that is called LSM bypass. So what is LSM bypass? This is a technique that allows you to actually access the core KV store directly. if you figure out that the data version that you need resides there exactly. So only in some cases in which we need to do a little bit more work to figure out the right version of the data, we go through the LSM. But really, in a lot of cases, like over 90% of the cases in many important workloads, we can improve the read latency through this LSM bypass technique. And the hard part about it is that we want to follow strictly the RocksDB API semantics, snapshot, checkpoints, and everything. So this is the hard part about the implementation. Okay, so we'll be rushing through some numbers just to show some of the advantages you can get with XDP-Rocks, both at the micro benchmark level and at the application level. So this, in this example, we emulate the workload of one of our customers running multiple databases on two SSD drives. So it's a write-only workload. So in this context, we see there is about 5x performance improvement in terms of throughput, and almost 100x performance improvement in terms of tail latency. So the other important metric is, of course, the CPU use. So in that regard, too, we since we crunch so many more operations per second, our normalized CPU per Kops fraction is also very low. Okay, so let's visualize this example a little bit. This is how the execution looks over time. The system's throughput looks over time. So those of you who work by day with RocksDB, of course, are familiar to the phenomena of compaction stalls. The system throughput is very jittery. It can come down to a halt and remain like this sometimes for seconds. With XDP-Rocks, it's a much less noisier picture. So we are both around 6.5x better on the average on the throughput side, and we are also much less jittery. The variance is just about 2%, versus RocksDB's variance is about 31%. And by the way, this is not the worst situation that can be demonstrated for RocksDB. If we put all the RocksDB databases into one and serve about 7 terabytes of data from a single LSM tree, the gap would have been much bigger. Okay, so naturally, you know, on the right side, the gap grows as the data size grows. That's no wonder. When you do key value separation, there is less and less data to move around. And so let me conclude the benchmarks part with the application level benchmark, also to maybe get you more convinced that what we do also does a good job at the application part. We picked a particular key value storage application, a service that is similar to ZPDB. KV-Rocks is a very popular key value storage software, popular in China, for example, supporting the Redis protocol. So we ran a variety of workloads on top of it, both the random fill and the random update workloads. So the improvements that you see are in line with our expectations from the micro benchmarking experiments. So when we move to more realistic mixed workloads, the gap is even more pronounced. So as you see, for example, in 50% read and 50% write workload, the excuse me, the RocksDB-based performance stalls at about 10%. The maximum throughput the system, the XDP-Rocks based system delivers, and the tail latency also remains very low. So to summarize, what we'd like to see is the world moving in that direction of specialized hardware, data accelerator hardware, delivering end-to-end application performance improvements to more and more applications. The one that we've seen today and many other experiments showed about 10x improvement in throughput and in order of magnitude more in terms of tail latency. What are what are the things that that inhibit this progress? The things that the main thing that inhibits this progress is that key value stores are basically an uncharted territory. There is no widely accepted standard that that would standardize the APIs, like for example block storage or TCP/IP. In this sense, open source projects like RocksDB are closest to the standards. That's why we want to be RocksDB friends. We want to promote this API and make its implementations even faster. So if you, we know that there is a session on RocksDB Vision later today. So we are not sure where this discussion will go, but if you ask me, what we would like to see is to have this project place a hardware accelerator as its first-class citizen. And it doesn't need to be something that is tied to a specific vendor's technology. It can be completely vendor neutral, that we work together to define what is it actually the specification that we'd like a hardware accelerator to deliver. So we're totally open about opening our code. There is a lot of IP to it. We love it, but still we'd love to contribute it to the open to the RocksDB community. The question is whether the RocksDB community is up to the challenge. So just a few words about where XDP-Rocks is going. So we are making inroads in the market, both with the end customers and with partners in this space. All of them are big. There are a lot of new applications that we are looking at, and no wonder, because RocksDB has done a great job of eating the world. So basically a lot of applications and services around the world are RocksDB based. So we are looking at a big variety of those. There is a slew of innovation in both algorithms and architecture that are coming up, making our system even faster. We are open to talk about some of them during the break. And you know, the last and not least, let me just reiterate what I said a minute before. We are totally open toward community development and open sourcing. We want to be friends with the RocksDB community. It's a long-term commitment from Pliops, and if you want to engage, let's engage. Thank you so much.
We have time for like a minute of questions, if anybody has any questions in person. Okay, otherwise, yeah, thanks.
Hi, Drupa.
Some benchmarks. In fact, those benchmarks, were they done on the same hardware or on the same price hardware?
No, same hardware except for the fact that part of them have been using XDP. Exactly same hardware.
Okay, so the question was, you showed some performance benchmarks. Were the benchmarks done on the same set of hardware, or were the different pieces of hardware for Pliops and
No,
Rocks?
the baseline was exactly the same. So we run exactly the same experiment on the same server, just with or without our card. Thank you.
Hello. I need to do this for the Zoom. Okay, that's a shame. So hi everyone. Thank you very much for joining us here. Thank you very much the RocksDB team for having us speak here. So we are Speedb. We aim to build the next generation storage engine. First and foremost, we are community facing, okay? We are a community-led open source project. We want to build with and for the community the next generation storage engine. So I'm assuming most of you, all of you are using RocksDB. It's already open source. It's already a community-based effort. We want to take it to the next level. We want to take contributions. We want to work together with you. And we want to hear your thoughts. And we want to hear what you think needs to be done next in order to get the storage engine that you need for your specific needs. Please join us at the Hive. This is how we call our community, the Speedb Hive. We are all bee-based, so the community is the Hive. It's a place where Speedb and RocksDB users can interact, can contribute, can talk, can discuss, can ask questions, can get answers. We have our own experts there. We hope more experts to join in and give any kind of feedback. Again, all questions are welcome, all comments are welcome, and definitely if you have any specific direction that you think we need to go, anything like that. So what is the current development focus for Speedb? We want Speedb to be high and stable performance, obviously, right? That is very clear. Everyone wants high performance, and everyone wants that performance to be stable. We want the storage engine itself to be stable, and we want the performance to get out of it will be stable. Obviously, we want scalability. We want to grow on a single instance as much as we can without losing the performance or without losing the stability. We want to build a versatile storage engine, which means a storage engine that fits to, I don't want to say any, but I want to say many use cases. So it needs to be versatile, whether in the programming language that we support or whether in the amount of use cases that we support, and of course, easy to use. One of the greatest things about RocksDB today, about Speedb today, is the fact that it has many, many knobs, right? It fits pretty much any scenario. However, the flip side of that is that it's not very easy to use, not very intuitive. Let's break down on how are we actually trying to achieve those goals. So first of all, at the bottom, you can see the link to our open source roadmap. Please go there. Please like or dislike specific features. We have a voting system for all of our features that we intend to develop. We want to hear the community. We want to hear the users. We want to hear what you think is relevant for your need, what you think is relevant for the storage engine need. And we will consolidate all of those comments, all of those voting. And with that, we will build a new roadmap over time. So we definitely want our roadmap to be customer-facing, community-facing. We want to build that roadmap with you. At the moment, what's in the roadmap, we have divided it into these 4 parts, right? High and stable performance, scalability, ease of use, and versatility. Every one of the lines you see there is already available as an issue in our GitHub. Already, some of them are available as code. The things that are pointed in blue are features that are already out. You can go to our GitHub, you can have a look. There's documentation on it, and there's the actual code in it, and there's the benchmark that we ran to show how much well it's working. I'll show you that soon. And the points that are in, I want to say purple, but I'm not that good with colors. These are things that we are actively working on now. which means, again, we are an open source development style company, which means you can join the GitHub and you can see the actual programming being done at the moment. Feel free to comment even there. If you see a bug waiting to happen, let us know. Let's not wait for us to finish and then find the bug. And the parts that are in black are the roadmap items. Once again, we really encourage you to join the GitHub and tell us what you think should be done next. I want to show you some of the things that we've already released in the Speedb GitHub. We have a different mem table. Basically, our mem table will not sort the data as it's being written, but does contain optimization for reads, which means you enjoy the benefit of very fast write without the disbenefit of slow reads. And you can see the performance of it in an environment with 1 billion key value pairs of 16K, with 50 threads on DBbench. The results are 17% gain on overwrite and 13% gained on mixed workload. This is already out. Please download, have a look, play with it, tell us what you think, tell us how we can do better. We have a new Bloom filter that we have designed together, co-authored together with Professor Niv Dayan out of the Academy. This is basically a Bloom filter. It's not a ribbon filter, right? It's the same old Bloom filter with a different way of calculating calculating it. So what I want to show you here is this. This specific scenario tries to imitate the read before write workload. And in the read before write workload, there is a very high importance to what is your hit ratio on the Bloom filter. So what we've seen here is 130% improvement on the read miss on read random, while all the keys are read misses, right? When all the keys do not exist. And to the same exact benchmark, we did the same amount of performance on less memory footprint. So our new Bloom filter will actually allow you either to run the same hit ratio or run with less memory, depending on what you need more. If you're in a memory-intensive environment, then you can lower the bytes per key and still get the same performance. Write flow is another thing we are working on today. Again, it's available in the GitHub to have a look what we're doing on it. We are changing a bit the way that the RocksDB write flow works. We are removing some of the locks, some of the mutexes. This is a work in progress, so I cannot commit on the actual results. But this is how it looks like today, about 30% improvements in overwrite and in read random with our new write flow. So, the one thing that everyone is talking about and the one thing that is very, very clear for everyone is that RocksDB is great. It's a great infrastructure product, but it is kind of complicated. There is a lot of parameters. And I showed you a few slides back, many of the features that we are working on in our roadmap to get the high performance, the scalability, the versatility, and the ease of use. The one thing that is missing is one big component to govern all of that, to make the best use possible of the existing features and of the new features that we are developing. And we think auto-tuning is the way to get that. So with auto-tuning, we of course need to monitor the CPU, the user behavior, the workload, the media, the memory, but we also need to take actions according to what we have monitored. So we are working in a two-phase approach. First phase is we're going to develop some features to work better, to improve the memory management, for example, to improve the CPU management, for example, to improve how much and how often do you write to disk, for example. And then on top of each feature, we will create some hooks to an auto-tuning mechanism that auto-tuning cannot live by itself. To just to auto-tune all those parameters is close to impossible, even though I know some other companies will say differently. It is very, very complicated. What we want to do is we want to take a bottom-up approach. We want to, and you know what, I'll do it now. So again, auto-tuning as something that entails the entire storage engine. Now, the auto-tuning need to consider application workload, CPU, memory, media, and we want to use it as an orchestrator for the entire storage engine. Now, the way that we look at it, and I want again to go for the bottom-up approach, zooming in on the memory, this is the amount of memory-related parameters we have in RocksDB today. Some of you are smiling, some of you know them, some of you didn't know there are that many, but they are. And actually, honestly, there are a few more. I was slightly polite here. Now, knowing all of these parameters is very complicated. Knowing how all these parameters interact with each other is even more complicated. Misconfiguring those parameters is extremely simple, right? We have a few cases from our customers that easily misconfiguring some parameters, so the num shard bits together with the cache index and filter blocks, caused all the indexes to get out of memory, and performance was just awful. So I see some nodding heads. You know it, it's complicated, it's difficult. What we want to do is we want to take a different approach to the memory altogether. We want to divide the memory into clean and dirty. So clean is everything that has been flushed, and dirty is everything that has not been flushed. Now, once we have a clean and a dirty memory, then we want to develop an overall or a quota enforcer on top of that memory. So it's way easier to say it than to actually develop it, but again, our approach is a bottom-up approach. So we want to create some intelligent memory optimization, some specific features to optimize the memory. We want to tailor all of these features into clean and dirty memory managers. And then once we have all of that complete, we want to create an overall governance of that, so a quota management to tweak the memory here or there as needed by the workload. And I want to take a specific example of something that we're doing, which is the proactive flush feature. This is, again, in our GitHub, almost done, so you can have a look at it, not done yet. This is a specific feature for a specific use case where we have multiple databases and multiple column families within all databases. And some of the column families in the databases has been written to, but then stopped before it hit the flush threshold, which means that we have stale data that sits in dirty memory and not being flushed. Until a new write will come to that database, that data will never be flushed. So we are developing a feature that will notice that scenario and then trigger the flush proactively to clean the memory or to flush the memory out of the stale column families. Once we do that, so before we do that, in this scenario, where we have a total size of 128 megabytes, a total size of 256, sorry, and the write buffer manager for, and the write buffer size for 128, so this scenario of 30 megabyte, 40, 90, and will leave us very low amount of memory for the last column families that we are actually writing actively to. And then as more that you write to that, you will initiate very small flushes that will cause very small compactions and so on. With the proactive flush feature, we will clean the CF1 in database 1 and the CF2 in database 1, freeing up more memory. Now, the intermediate results of that is this. So, of course, this is a specific scenario, but when we run the benchmark on this specific scenario, we see that when we hit that wall, when we hit the point where the last column family keeps on doing very, very, very small flushes, and we are cleaning the other column families, then it becomes quite more high performing and quite more stable. Now, again, this is up on our GitHub. You're welcome to have a look at it now. And we will appreciate your comments. It will be released, hopefully, in the upcoming version. And you can actually try it if your scenario fits. Now, this is a scenario that came directly out of one of our customers. They had exactly that scenario. And this is a feature that was tailor-made for a specific scenario. But we believe that this scenario is quite common in the community. So, to talk a bit more about the Dirty Data Manager. As I said, we want to take the entire memory structure, divided into 3, dirty, clean, and then overall. We want to do specific features to work on the clean memory manager. We want to do specific features to work on the dirty memory manager. And once we have them all, and they can report all up to a common overall quota enforcer, this will be the hook to auto-tuning, because this quota enforcer can actually auto-tune the memory. I'll touch that in a bit. I'm talking extremely fast because they only gave me 20 minutes, so sorry for that, but I'll keep on going. So in the Dirty Data Manager, we have the proactive flush. Again, as I talked before, hopefully very clear what it does. And on top of that, we want to integrate the delay mechanism into that proactive flush as well. So the proactive flush, I already talked about, and integrating the delay mechanism. will actually eliminate the out-of-memory risk and hopefully stable the performance quite dramatically in that scenario that I showed before and pretty much in every other scenario. So we want the delay write mechanism to be integrated within the proactive flash scheduler, and we want it to be a global delayed write mechanism and not a per column family delayed write mechanism. Once we have that dirty data manager, and of course we'll plant some hooks in it to report up to the overall data manager, we want to develop the clean data manager. So the dirty data manager is currently at works. The clean data manager will start next. In the clean data manager, we actually want to pin all of the indexes to the memory. We want to pin the recent mem tables into the memory. And then we want to dynamically remove the pinned data according to lower levels first. That is a naive view at the beginning, and afterward we don't want to do it with dynamic workload pinning. So we want to figure out which data has been read the most. We want to keep that data, or the indexes for that data, pinned, and then release from pinning the other data. Which means basically we're going to take LRU and we're going to put it on top of pinned memory. So we're going to do dynamic pinning, which is kind of funny because that's not the point. But from our basic testing, we've seen that this improved the performance quite dramatically because as soon as the data is pinned, the access to it is much, much faster. And we can assume which parts of the data we can unpin quite safely in terms of performance to actually gain further benefits. So once we have those two, the clean and the dirty, we'll work on the overall memory manager, which is actually the auto-tuning hook. This would be a component that all I said up until now was a lot of heavy lifting. There's a lot of work to be done to program those features. Once those features are done, we're going to enjoy the benefit of those features. So we have a clean data manager. We have a dirty data manager. They all standalone work pretty well by themselves. And then we'll build on top of them the total memory manager, which will allow us to control the clean, control the dirty, understand the system. Are you a write-oriented workload? Are you a read-oriented workload? And actively tune, do we want more data to the clean, or do we want more data to the dirty? So basically, we will control the parameters we'll get from the user, what is the clean memory size, what is the dirty memory size, and what is the overall memory size. And then based on system behavior, we can allocate more data to dirty or more data to clean, depending on your use case or depending on the user parameters that you put in the system. Our vision is build a performant, scalable, adaptable, easy to use data engine for every workload. I want to really linger shortly on each one of those words. So performance is very clear. We want high performance. RocksDB is high performance. We want to keep the high performance and improve the high performance. We want it to be scalable. We want to be able to scale on a single system quite dramatically. The more, the merrier. Of course, you still need to shard it. Of course, sharding is something you might need to do, but we want to give you the chances either to postpone it or to have larger shards. We want it to be adaptable or auto-tunable. We want it to fit many workloads or versatile. We want to have the storage engine fit many of the use cases. And we want it to be easy to use. The wish is auto-tuning, right? Everything will be self-configured, totally alone, very intelligent AI. Now, that is the wish. Our plan to go there is bottom-up. Specific features that will report to an oversized feature, that will report to an overload feature, and eventually we can build an auto-tuning system. We do offer support, the entire point of Speedb going open source, the entire point of our Speedb Hive is to give community support. We welcome you to join. We welcome you to contribute. We will accept the PR, not just we accept the PR, we are asking for PRs. Tell us what you need next. Tell us what is interesting for you. That is what we develop. Develop for us, we will integrate it, and we will, of course, continue rebasing on top of new RocksDB versions. We are offering community support. You can join our Discord, ask anything. If you will be forthcoming with the information, we will be forthcoming with the answers. We'll even build mini labs to help you answer your question. And we have our enterprise-grade support for enterprise customers. I welcome you all to join our open mic night. Mike Dorfman is our co-founder and chief architect. We are holding a monthly open mic night. In that open mic night, we will open a Zoom for everyone to join in, and everyone can ask whatever question they want. preferably regarding Speedb, RocksDB, and not general questions, but we have quite a large general knowledge as well. So join in, ask your questions. If those questions are extremely complicated, extremely deep, either we'll ask for logs and we'll review the logs together with you guys live, and we'll think together, or we'll take it offline, but join in. Ask whatever question you want. Ask me anything, or not me, but Mike there. He loves his picture up, so he's smiling. And the next one will be on December 15th. We invite you all to join. Come with difficult questions prepared. Thank you. Oh my God, I did it on time.
All right, guys, we have a 15-minute break, so please, get a drink, use a restroom. There's swag in the back, and come back in 15 minutes. I'll give you guys a 5 minutes heads up. Thanks.
My lover's got no money, he's got his strong beliefs. My lover's got no power, he's got his strong beliefs. My lover's got no fame, he's got his strong beliefs. My lover's got no money, he's got his strong beliefs. Want more and more, people just want more and more freedom and love. What he's looking for, want more and more, people just want more and more freedom and love. What he's looking for, freed from desire, mind and senses purified, freed from desire, mind and senses purified, freed from desire, mind and senses purified, freed from desire. Na 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 My lover's got no money, he's got his strong beliefs. My lover's got no power, he's got his strong beliefs. My lover's got no fame, he's got his strong beliefs. My lover's got no money, he's got his strong beliefs. Want more and more, people just want more and more freedom and love. What he's looking for, want more and more, people just want more and more freedom and love. What he's looking for, freed from desire, mind and senses purified, freed from desire, mind and senses purified, freed from desire, mind and senses purified, freed from desire. Na 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 na
shake it, lean back, bounce. Lean back, shake it, lean back, bounce. Shake it, lean back, bounce. Lean back, shake it, lean back, bounce.
We should be loved. You know, some people just get fooled. Some people get schooled. Some people get outlawed, you know. But in front of the Almighty God, we're all the same. We're all God's children. And we are the parents, so we must be the fathers and mothers of the children that's going up, so we have a brand new love generation. Love generation. Come on.
Hey guys, we're going to get started in 2 minutes, so if you guys can grab your seats, that'd be great. Thank you.
Don't get hooked up on what you see, because the greatest thing is spirituality. Share that love, come on, share that love, come on, share that hope, come on, share that dreams.
Hey, let's go ahead and take our seats. Thanks, everyone.
Hello, everyone. My name is Sandeep Madanala. I'm a senior technical manager in the core database group at Nutanix. Today, I'm going to share our experiences and journey with RocksDB at Nutanix. We started using RocksDB because of its distinctive features, such as embeddable, pluggable persistence layer, and open source support, among others. In this talk, I'll give over how it has evolved, our learnings, and some numbers, followed by Q&A. So we started using RocksDB as a single instance embedded database to store a fraction of our metadata in Nutanix distributed file system. However, with growing use cases across several applications, we went on to build a high-performance, linearly scalable, cloud-native, distributed key-value store called ChakraDB using RocksDB. In the interest of time, I will not go into the details about why we developed this new database instead of using any existing open source databases. The motivation behind building ChakraDB is explained in the two-part series blogs, the links to which will be provided in the slides. Without much ado, let me talk about how ChakraDB uses RocksDB. ChakraDB incorporates virtual nodes-based sharding design, which enables linear scalability with high throughput and better tail latencies. This provides flexibility around data movement and placement. Virtual nodes design makes the cluster truly elastic, as it can be expanded or shrunk seamlessly by simply moving around the vnodes. So this is how a single ChakraDB instance looks like. It is a single process that embeds multiple vnodes in it. These instances can be scaled linearly to form a ChakraDB cluster. As we went along this journey with RocksDB, we found that as the scale of our deployments grew, gaps started showing in our system. We started seeing performance and stability concerns as DB sizes approached hundreds of gigabytes. Let me walk through each of them. When the DB size goes into billions of key values, the garbage can go into order of millions of keys, at which point we saw RocksDB scans taking minutes to complete, by which time the client would have already timed out and would have sent a retry. This led to retry storms where we would be executing several scans for the same client op, putting pressure on the resources. We introduced circuit breakers on deadlines to mitigate this. However, it did not solve the problem of scan unavailability across the cluster, which meant the duration of unavailability for scans is unpredictable. To address this gap, we brought in a new component called Background Task Manager in ChakraDB. Its chief responsibility was to track the garbage and take corrective actions as needed to keep the scan unavailability as low as possible. It proactively polls RocksDB to calculate the amount of garbage and decides if it needs to trigger corrective action. In case there is a delay or gap not covered by the heuristics, we also have a feedback mechanism from scan, wherein a failure due to garbage will always trigger a corrective action. Corrective action may need a combination of flushes and compaction if the tombstones are mostly in memtable. At the same time, it involves a compaction if the tombstones are mostly in the on-disk SS tables. Now, coming to improving the read performance, one of the limitations to increase the read performance at scale was that the read APIs such as get, multi-get, scan APIs is that they're all synchronous in nature. So client threads issuing reads are blocked within RocksDB while reading from the disk or acquiring DB logs. Our requirements from the API was to allow asynchronous programming model to be used for better thread utilization by avoiding to block physical threads for disk IOs, network IOs, or while acquiring logs. This model allows us to achieve the same or maybe better performance without shredding too many threads to the process. To achieve this, we utilized Nutanix fibers, which are coroutine-style, cooperatively scheduled application threads. Each fiber has its own CPU state and its stack, but needs to be scheduled on a host thread, such as a POSIX thread. When a fiber needs to block waiting for an event, it returns control back to the host thread, which is free to pick up some other work. With fibers and Linux asynchronous I/O, we were able to design non-blocking reads using vanilla RocksDB code. Through this, a single thread is able to provide multiple outstanding I/O. I'll keep the numbers for all our improvements to the end in the interest of our time. We see a similar issue with the write path as well, where we saw that the follower threads of an active write batch group, like F1 and F2 in this example, spin for a while, followed by blocking themselves until the leader thread does a bunch of work for the group. And the write threads which enter while there is an active write batch group, like F3 in this example, gets blocked till the previous write batch group completes. While reader is writing to the wall or the previous batch group is completing the work, there is a lot of CPU wastage. To overcome this problem, we started batching writes in a layer above RocksDB. Client threads adds work along with the write done callback and returns. There is another thread in the RocksDB layer which groups all these requests and send it to the RocksDB. With ChakraDB, we can spin up multiple RocksDB instances in a single ChakraDB process or an instance. This can quickly take up a lot of memory. We wanted to deterministically control the memory usage both in steady state and also during the background operations with such a bunch of improvements such as sharing the block cache across multiple RocksDB instances so that we can control the overall usage in the ChakraDB instance. Keeping a threshold on the overall memtable usage by all column families across RocksDB instances using our background task manager again. Memory bloats during compaction used to be a consistent issue at scale. Along the way, we learned that for larger workloads, moving from a single level to multiple level helped us in restricting the resource usage across the cluster. At the same time, we also disabled filters at the last level because we realized the majority of the workload usually stays in the last level. This came up with a con that there is a slight impact to the performance of the negative lookups, which we were fine with. Again, to restrict the memory usage during universal compactions at the upper levels, we relied on a background task manager which intelligently tracks the memory usage taken by the compaction for all the upper levels. And we put a threshold there, and beyond which the background task manager comes to the rescue and triggers a compaction, moving the data to the last level. Maybe we should no longer name it as background task manager. To further handle with the write amplifications and space amplifications, see, we also explored the RocksDB code to see if during the compactions, if there are any SS tables with non-overlapping key ranges across the levels, we move the files instead of reading and writing the files over and again. This helped us in reducing the write amplification and space amplification. This work, though it's not still in production, but it gave us some promising results, and we are in the works to put this into production. Some of the stability improvements include detecting corruptions in the manifest file. Now to do that, instead of storing just the file name in the current file, we started storing the manifest file metadata and also its checksums. This helped us in detecting corruptions, which are very critical for a lot of applications. With current set of improvements in place, we are also looking into other areas like throttling the bottleneck background operations to limit the CPU usage and add the support to tier cold data to remote storage, among other things. And looks like RocksDB community is already working on some of these things which we want to leverage. Coming to the numbers at some glance, as you can see, with our asynchronous reads, we are almost able to achieve the same performance or similar performance with lot less threads with fibers enabled as compared to synchronous IOs with number of threads equal to the number of outstanding. These are the right batch improvements with and without batching. Some of the benefits that we have observed are the throughput increased by a large margin. At the same time, client threads are not blocked. We don't need to scale more threads as we increase the number of outstanding. One of the cons that we have seen is we were losing out on the parallel memtable writes, but again, it was not showing up in the performance. These are some of the scalability numbers. I mean, right now, where CheckRDB is in production in some of our clusters with Nutanix objects, and right now we are working in to put it in production with Nutanix distributed file storage. I have only 10 minutes of time, so I'm rushing through a bit. But this slide shows that the scalability or the throughput increases with number of instances in the CheckRDB cluster. Here is a team at Nutanix that works on RocksDB right now. So feel free to reach out to any of us for any questions or queries. At the same time, you can also reach out to rocksdb@nutanix.com if you have any more questions. Thank you. That's all I had.
Hello. Hi, I'm Sling from Meta. So here I'm going to give some introduction about our long-term plan of RocksDB. 3 years ago, in the roadmap, in the meetup here in the Meta headquarters, I gave a presentation about the exact plan, long-term plan for RocksDB. Now it's 3 years has passed. A lot of the plan work has been done. So I thought it would be interesting to give some review about what we have achieved according to the plan and present about the plan for the next 2 to 3 years. So starting from the mission, so 3 years ago we talked about our mission is to create a fast and easy to use persistent storage engine for any workload on any hardware platform. That means the generic and for application, generic for hardware, and the performance well and easy to use. I think that's we revisited, and we think we should we will keep this version at this moment. So first, let's review the plan I presented 3 years ago. This is the exact slides we presented. We talk about we would focus on 5 areas: remote storage, data integrity, performance and efficiency, ease of use, and new data models. I will go over them one by one. Remote storage, and 3 years ago, we said that an important trend was to move RocksDB to work on remote storage. That means something like HDFS, S3, or something like that. So we listed some of the planned improvements to work well, and we said that we would need to work on transient failure, because that's new for us. I think we did a lot of work to for RocksDB to handle transient failure and try to keep up. And we said we will do batch and parallel I/O. We did parallel I/O for multi-get, async iterator reads, and adaptive iterator read ahead. I think Anand Kengsha will talk about this more later today. We thought we would need to do, we tolerate longer latency. We built some of the features to pass in the I/O deadline all the way to the story layer and do some asynchronized I/O prefetching. And we also thought we need to do some toolings. We did improve our I/O tracing tool, in I/O tracing facility, and some of the tools to work with as remote storage. The plan was to not just survive with remote storage, but to take advantage of the great features with shared storage. We plan to work on disaggregated compaction. I think the features is almost there, ready to use. It's called remote compaction. We also thought it would be interesting to have secondary reader to read from the same data from the remote storage. And I think the feature is ready to use, although it lacks some features like catching up the latest reads, but it's in the state ready to use. We mentioned that tier storage, which means hard drive and SSD hybrid, was a great feature to work on. I think we made some good progress on that, and we will invest on more going forward. The last thing we talk about fast DB cloning, which we have some support for RocksDB already, the checkpoint something, and we didn't do much specifically for shared storage yet. So that's the remote storage section. I did a lot of work. Another area, the second most important area we thought we would focus on was data integrity. I think we said improving testing was an important thing, and we did improve our stress test coverage significantly. We cover a lot of more features and also cover more failure ingestion cases and crash recovery safety testing. And we also have some recent cool features like ingesting, sleeping after mutex grabbing, mutex releasing things. So we have lots of test improvements. We said that we will control when the data will be physically gone from file system, rather than just tagging it as deleted as tombstone. When this physically deleted is gone. We created two features, one called TTL compaction, one called periodic compaction. That's to guarantee for people to have some control when their keys will be passed to the last level or go through compaction filters to make sure that the data they deleted will be gone. We said we will have a physical checkpoint of the whole files to help people to check file integrity after file is moved over the network or go to another storage, and I think that was implemented. We said we will implement per key value checksum. I think we made some progress. The mem table part is implemented, and the block cache part of key value checksum is underway. The only thing we mentioned 3 years ago we would work on, but we didn't make much progress, was encryption at rest. So this part we didn't make lots of progress, but we did make lots of progress for our planned work for data integrity in the past 3 years. So next areas is always important for us is performance and efficiency. So we said we will work on BlobDB, which is a key value separation solution. I think this is we made great progress on this. It's almost support all the features already, and then quite reliable now. And we said we will improve Bloom filters, and we did. And Peter did great work to improve CPU usage for Bloom filter, and we came up with alternative filter called ribbon filter, which is more memory efficient. We said we would reduce DRAM and usage and CPU. We made quite some improvement in these two areas. Of course, this is a never-ending job. We said we would improve latency for long scans, which we did take a look, but we didn't do a lot at this moment. We will probably look at it in the coming years. We said we will improve locking in block cache, and we did implement a new feature called hyperclock cache. It's a re-implement of our clock cache, which is widely believed to be friendly to lock contention, and then this is ready to use. I think it's used in production already, so feel free to give it a try to reduce CPU and the tail latency once there's hotkeys or hot blocks. Finally, we said that we would consider garbage collection in memtable because there's some workloads that keys keep being deleted and working set is small. We don't want to flush those data if they are in memory. And we have a feature called mem purge implemented. I think it's ready to use, right? You can talk to Peter if you are interested or have interest in this garbage collection in memtable. So this is performance and efficiency section. We have this ease of use, not finally. So we list some of the features we plan to work on. Adaptive compaction, well, this is a feature that we've been trying to work on for 10 years, but unfortunately we didn't get there in the past 3 years. We said we would have stricter DRAM cap. We made lots of progress. Akanksha's here. Akanksha will probably, you can talk to Akanksha. Sorry. Hui is not here, yeah? But you could talk to Andrew, I guess, about we did lots of work to cap DRAM more efficiently. We didn't come to the feature of stricter max background thread cap. We did implement persistent stats and trace and replay. And our previous teammates, Zhizhao is here, implement this trace and replay. So it will help. It's a good tool to help people to understand the workload and then replay this offline. And the tuning advisor we listed there when we never got there. And we set more adaptive algorithms, and we did make some algorithms more adaptive here and there. So that's the ease of use section, and then we did some good progress on this. Okay, so then future plan. This is going to be next 3 years or so. So we think that it's still mostly for these 5 areas, although the first areas moved from remote compaction to a more general new hardware program. That we still think that's the areas we should work on. Let's go over them one by one. So first one is the new hardware platform. So this time we are going to focus on the 3 kind of hardwares. 3 kind of hardware. First is continually disaggregated storage. We have its functioning work, and then in production, quite large scale, but we still have more work to do. We need to continue the performance optimization in different ways. We need to continue our work with the remote compaction and the secondary reader instances. So this is the disaggregated storage. We still have lots of outstanding work to achieve to realize the benefits from it. Another hardware platform we plan to focus on is tier storage. We briefly mentioned 3 years ago, but this time it's going to be a major thing for us. Is to hybrid hard drive and SSD, which made it possible by disaggregated storage. So the status right now is we have a basic implementation that you have a last level stored in hard drive, other level in SSD. And then when doing the compaction, We keep old keys, means that users specify how old the key is, the threshold, that's 7 days. After 7 days, the data will be compact to last level on hard drive and other keys in higher levels in SSD. So this is the current implementation, and we will need to work improve on this. We will need to implement a more sophisticated prediction, key value pairs is code or not just by timestamp. I think Jay will introduce what we have now for this tier storage, hopefully later today, we will need to do some more sophisticated prediction of per key value coldness, and we probably will need to find a way to keep index and filter blocks in SSD, even this is for the cold data. And we also need to deal with the case that if the cold tier has some hot data, how do we deal with this? We either move it or cache it or both to figure out. And also there's a performance for run queries or some other workloads we need to figure out how to deal with this. So another hardware platform we will work on is the new NVMe interface. I think Meta collaborated with Google to propose to reduce write amplification. If you are familiar with things like ZNS, this is kind of the similar stuff. We will make sure that RocksDB will enable those the lower layer, storage layer, to take advantage of this. The current thinking about the way we leverage lower layer to implement this is to predict each file's how long it will live when creating the file, and pass that as a hint to a lower layer so that they can do the placement accordingly. So this is the hardware, 3 hardware platform. So next area is new data model. So we will continue our user-defined timestamp direction, which is other than key and value, have another timestamp. You can imagine there will be some MVCC support that different version of the keys will be treated as first-class citizen, and using that, the performance can be better. And then there's a white column. This white column is a term for those data models similar to HBase Cassandra, which means you have a key and then a column, but the column is not predefined, but arbitrarily you can use online. And since we have white column, and then we would try to explore some higher level schema support on top of columns. Maybe types, maybe secondary indexes, or maybe make it easier for application to implement tables or indexes. So basically more work on top of the white columns. So the third area is performance and efficiency. So this time we would continue our CPU and DRAM optimization. So that's always efficiency. CPU and DRAM are we think about an important resource. We will continue our improvement to compaction, and compaction is a core component to RocksDB, or log storage tree, as you all know. But we didn't have a lot of major changes to compaction. We should catch up this area. I think we are already doing some of the exploration to level compaction improvement, and we're thinking about this incremental universal compaction. Universal compaction have limits of you have to do the full compaction all the data, which will take a very long time, and doubling the data. Have issues. We were thinking about making it incremental, so cutting into smaller pieces. And finally, there's things we plan to do is to have a unified compaction to serve both use cases, so that people don't have to pick which one. And if their workload changes from read heavy to write heavy, or vice versa, they don't have to do very expensive migration. BlobDB, this is the key value separation approach, and we hope to continue closing the gap of what features not working with BlockDB, and make sure that they just work with everything, so that your users can just adopt it easily. Yeah, and finally, we realize a lot of data are in the nature of the time series. And by that I means that data is kind of TTL, like data lives in 7 days or 14 days, they're gone. And then, so if we know that RocksDB knows the information, that data is kind of FIFO, mostly FIFO, that the compaction could be made more efficiently rather than just blindly merging all the data to reduce performance. So this is the performance and the efficiency section. Data integrity, that's always important, especially it matters these days. So for data integrity, we'll keep improving stress tests, as what we have done in the last 3 years. We need to finish our plan for per key value checksum, as we already started. We probably will need to explore fuzzing tests. Our current stress test is based on randomization, right? Just randomly pick up these set of options and randomly generate workloads based on the predefined list. That randomly could give us great coverage, but might only get us so far. We're thinking about maybe some fuzzy test for at least for some component that might get us some more coverage. Formal verification. We think about some components might benefit from some formal verification. Verifying the whole RocksDB probably is impossible job, but some component like the compaction, the file lifecycle management, or even some of the format might benefit from formal verification to make sure that the algorithm is correct. Finally, encryption at rest. We always think that is important. Hopefully, in the next 3 years, we'll be able to get there. Or if someone is more interested to help us, you can help us. Yeah, so finally, it's ease of use. Given that we have such a large user base, making it easy to use is always important. So we will continue our execution of past several years of improving out-of-box performance and makes knobs simpler. We have been working on this constantly to see which default will be good, whether we can remove this option. We will continue that. And I mentioned that we hope to have a unified compaction, but unified is not just enough. We also need a more adaptive, just based on the workload. The compaction just adapt it to your workload. That's always something we plan to do, but I think maybe we are ready now to think more about these things. We have improved filters, but we could have automatic filters in various ways. We could automatically determine whether each file needs filters or not, or how much memory should be used for this file's filter. We can also determine whether the file needs range filter or prefix filter, and then how many the number of bytes used for prefix filter. These all could be done automatically, and it could be also even smarter to make it more automatically. And we need to be more adaptive resource management. What we have done for memory is a good example, and we will continue the memory management adaptiveness, and then probably some other resource like background threads and IO. We could make it more adaptive. Okay, so that's everything we have. That we will work on these 5 areas and continue making RocksDB a fast, easy to use, persistent storage engine for any workload and any hardware platform. Yeah, thank you for all the contributions you made. Was I out of time or?
Yeah, we're good. So
Okay.
I think Luigi is next with DBtune. So
Okay,
thanks, E.
Okay. And
Let's take questions after because we're on time.
okay. Sorry.
Hi, can you hear me? Yes, how are you doing? So today we're gonna talk about, not Meta, but DBtune. So DBtune is a database tuning software as a service. We've been talking about auto-tuning in a couple of other talks today. And we have a solution for this. So this is ready to be used for Postgres, and now we're extending it to RocksDB. So we have already been running this on RocksDB internally, and we will be opening this side of the product as well sometime soon. What I'm trying to do today is to find adopters, early users, and partners, right? Right, so databases, as you know, they change, they grow, they slow down over time. So the process of keeping the database fit and responsive is called tuning. We call it tuning. Somebody calls it auto-tuning as well. And the process looks a little bit like the picture on the right. So you have all these different knobs, and what you're trying to do is to find the best combination of those knobs in a way that you achieve high performance, right? As simple as that. The issue, though, is that if you look at this problem over the years, and you look at, for example, MySQL, of course, RocksDB is only 10 years old, but it's going also in that direction, right? The trend is the same. So you look at MySQL in 2001, you had about 100 knobs. You look at MySQL today, you have 600 knobs. Of course, many of those knobs are not really important for performance, but some are. And the issue here is that this is an exponential growth of potential possible configurations, right? So solving this problem for 10 parameters is very hard, but solving this problem for 11 parameters, just one more, is exponentially harder, right? So we need to find a solution to this problem because this is becoming out of hand. So the things we usually care about are throughput and latency, so in terms of transactions per second and average query runtime. And of course, these two things also affect things that perhaps the business department cares about, which is cloud and infrastructure savings. So I will not go too much into that level of detail, but very often what we see with our customers is that if you can accelerate your calculations, you can pretty much turn off some instances, and then you will have a better bill, AWS bill at the end of the year. So we're talking about very substantial savings in that sense. You can also, of course, save by having a more efficient data operations, like the complexity, reducing complexity. So your DBAs will be, busy doing other things than, a task that can be fully automated. At least this is our take on this. And of course, if you make your pipeline optimized, you also have great energy savings, which are kind of becoming really, really important now in this current ecosystem of greenhouse gases, cap and trade markets. So the problem today is solved manually, mainly. So there's a person sits down and spends often several days to just optimize one instance. It's a very slow process. It's very ineffective usually. If something changes at the application level, then you need to do this again. And usually it's good to do this again and again and again. Of course, we don't do this again and again because it's a manual tuning process. But what happens if you can actually automate this? Now it's a push-a-button solution, so you can run this as much as you want, whenever you want. And there are on some other database management systems, there are some other expensive proprietary tools, and there are also some DIY tools. For example, in Postgres, PGTune, for example, is an open source that allows you to tune the parameters. The issue with that class of tools is that they are always giving you the same answer, no matter what the workload is. So we would like to fix that. We would like to have an answer, meaning a configuration for your database management system that depends on the specific usage that you're having, and application level and the machine, specifically the machine you're using. So we're hearing about hardware acceleration before, and it will be really cool to actually mix the database management system knobs with the knobs of the hardware as well, which is something we are also looking into operating system level wise so far. So I'm saying that to date, there are no automated solutions for RocksDB. Perhaps the talk before by Speedb was going in that direction as well. It's very exciting. Looking forward to talking with you guys more on that. So this is how it works. So on the left, you have your database instance, and it's going to be on-prem or a cloud instance. You have the DBtune controller, which is composed by a monitor that just basically pretty much gets the performance of the database instance. So throughput, latency. We measure as well CPU usage, RAM, and disk IO, IOPS, things like that. And then there is an actuator which merely takes the recommendation that comes from the optimizer and just actuates that configuration. So on the right side, you have the optimizer, which is based on prior learnings, right? So this is about trying to use all the knowledge that we have on that problem to inform the machine learning models that are the recommendation models used by DBtune. So the recommendation models start this optimization by providing a first recommendation. Of course, the first recommendation will be a little dumb, perhaps just based on the prior learnings. But then what happens is that this configuration is run on the machine. You collect real-world data, and this data is then integrated in the machine learning model, which will become better and better over time. And so eventually, the machine learning optimizer will become good enough that can provide an approximation to the optimum of this very complex optimization space. So this is a feedback loop, right? So you start from the optimizer, you go, you run this, you observe, and you go on a few times, and then the optimizer gets good enough that tells you what's the final recommendation, right? Right, so the four, value propositions here is that this is a tedious process. You can fully automate it. You free up your database administrator's time. This is usually, a 20–25% of a DBA time, right? So DBAs are busy doing many other things, so you can save time for this, and they can really focus on the things that are more important, right? So this is the first thing, so reducing complexity. The second thing is reducing cost. By reducing complexity, you also reduce costs, but you also reduce costs in the sense that perhaps you need less database instances running to serve your clients if they are fully optimized. And then we make the service radically faster, right? And we save energy consumption as well. So just a little, we have plenty of data on benchmarks. Here today, I will just give literally one plot, but just to give you an idea what this looks like in terms of RocksDB. I've been running this on Google Cloud Compute. The benchmark is a pretty common benchmark, 90% reads, 10% writes. Configurations are changed through CLI. We tuned 13 parameters here. 13 parameters means 10 trillion possible configurations, 10 trillion possible configurations. Now imagine a DBA that is now optimizing the space by hand and needs to try 10 trillion possible configurations. Of course, it's not going to be possible, and they're going to try perhaps 10 or 20, and then they have to come up with the optimal solution, which is a very challenging task. And human beings are not really good at this. We have to admit that, right? So we have models, we have mathematical modeling that allows us to do that in a very meaningful and Bayesian way, right? So you learn from your past experience. So looking at the performance, we get the default, it's under, so we have on the y-axis, we have the operations per second. I'm comparing default with DBtune. We get 104,000 operations per second on the left, and DBtune is under 65,000. Higher the better. Here is throughput. So this is a 58% improvement over default, right? So this is a sizable amount of performance that we squeeze out of just optimizing parameters, right? As simple as that. We focused originally on Postgres, and we have a product that you guys can use today on Postgres, and we are looking forward to providing the RocksDB part as well. And we are rolling customers on Postgres right now, and we're looking forward if you guys want to try the RocksDB internal version as well. That would be really awesome. Just a little demo. I wanted to give a live demo, but I wasn't allowed to do so, so I will just run a little video here very briefly. So this is the login. You see here on the left, you see 4 database instances that have been optimized with DBtune. You can see the opinions benchmark, the first 2, and then you have the resource stressor, 3rd and 4th database instance there. So what you see here is the dashboard of DBtune. So you get throughput here on the y-axis. You have throughput, and this is the optimization real-time data. You can trigger CPU data, RAM data, disk data, and then this is a summary of the optimization. So here are all the configurations that the system has run over time, and you can find the best configuration, which is that one highlighted there. And this was the default configuration. So you can see the gap between the default configuration and the best. This is a speed up of, I think, 6. I cannot really read that far, but I think it's 6x speed up. So very excited to talk to this community today. Please join me for the coffee break and let me know what you think. Thank you.
Hi, I'm Peter. I'm work here at Meta, and I'm going to talk to you about Hyperclock Cache, which is one of the things I've been working on with my summer intern, Guido, built the first version of this, and I kind of took it to the next level. And I've collaborated with Anand and Mark Callahan with this on this also. So we're going to talk about CPU efficiency and scalability. RocksDB has a history of, taking this very seriously, and one of the big things you do for your workload scaling to many parallel processes is you migrate away from mutex-based algorithms and move to lock-free algorithms. We have a number of places in RocksDB where we did that about 7 years ago, but we've had this one lingering area that's really crucial to the read path. That's the block cache, and it's been hanging around as mutex controlled. Fortunately, it is a sharded mutex structure, so on average you don't have a lot of contention to deal with, but in corner cases you can deal with a lot of contention, especially if you have like one hot block and a bunch of CPUs are contending for it. They'll have to wait on each other even to read that block. So that's kind of the problem we're trying to solve. Better CPU efficiency and scalability. So let's look at LRU cache in a little bit more detail, and I'll try to be quick about this. Basically, all these arrows are levels of indirection. These are pointer indirections. So there's a lot of indirection going on here, and we want to improve the efficiency. Hopefully, we can reduce some of this indirection. Let's focus in on this area that I've highlighted, kind of the second and third level of levels of indirection that are controlled by this mutex. Everything else to the right is kind of immutable once you refer to it, and so it's kind of these 2 levels in the middle here that are most interesting. And the reason it's mutex controlled, basically this is a hash table, and the cache shard points to a raw table, which is like an array of pointers, but that needs to be able to grow because even though the block cache has a fixed capacity, we don't necessarily know how many blocks that capacity is like an amount of memory. We don't know how many blocks that's going to correspond to. So we need to be able to grow to that number, or at least it'd be really nice if it can just kind of adapt. So periodically, if our table gets too full, we need to, like most any other hash table implementation, create a new table, migrate to that new one. But that means we need the mutex controlling access to the table so that we don't have some thread that's holding on to a stale pointer to the old table and run into issues that way. And then we have these handles which keeps track of how many references are pointing to this block, that sort of thing. And it uses it's a chained hash table, so that can lead to even more following pointer indirection. One possible solution to this is something called hazard pointers, but it's not great in this situation because it doesn't really guarantee that things are freed once you immediately upon saying that you don't need it anymore. But we're going to kind of strip the block cache down to the minimum that we need. And step one for that is, can we get to a point where we don't need any synchronization to get to a handle for a potential block cache object? And the way we're going to do that is first we're going to break one of those features that I said was useful, but I think in many cases we can guess how many block cache entries we're going to have based on the capacity that you've configured. Usually you set your block size. That's a good predictor of how many of your average block size. So hopefully we can predict this ahead of time. And so if you're willing to fix at creation time how big your block cache is going to be, or how many entries are in your block cache, we don't have to worry about this problem about chasing a bad pointer, and we don't need any synchronization to get to the raw table itself. The second part is we're going to inline the handles into the table rather than allocating them dynamically. And one of the requirements for this is right now, or in the old days, block cache keys were variable size. So one of the reasons that we dynamically allocated the handles was we didn't know how big the key was going to be. So we would allocate the size of the handle based on the size of the key. Well, I went through a project to make the block cache keys of fixed size so that we could do something like this in part. And so now we can just say, okay, instead of allocating a table that's a bunch of pointers that point to dynamically allocated handles, the table itself contains the handles because they have fixed size keys. All right, and so that gives us, we can get to a handle and don't have to worry about an invalid pointer because of synchronization issues. So that's kind of the first part. And then the second part is what we do once we get to a handle. And we want efficient ref counting and tracking metadata for eviction. And basically using clock instead of LRU, we can, and some clever encoding of ref counts. So if you look at line C down there, basically instead of explicitly tracking the ref count, we have a counter for the number of acquires and then a counter for the number of releases. And the ref count is the difference between those two. But it means when I touch an object, if I increment the acquire count, that tells me that I've incremented the reference count, but it also tells me that I've recently accessed this data. So basically every access to this cache is almost as in kind of the average case, it's like another reference to a shared pointer in C++. It's very lightweight. And that's, borne out in some of the data. You can go look at Mark Callahan's blog post about this. For really hot, you really see the benefit in like really hot read use cases where most of your reads are handled by the cache, block cache. And you can see with lots of parallel threads, you get a really big performance benefit versus LRU cache because of the lock-free, very low contention benefits. Yeah, some next steps. Hopefully I'll be writing a blog post about this and adding secondary cache support. I have in the works a version of this that will do that won't rely on that prior estimate of the block size. But as you can imagine, it's kind of complicated and still a work in progress. Yeah, I think that's about it.
Hey, my name is Jay. I'm a software engineer, and today I'm going to talk about tiered storage and time-aware tiered storage in RocksDB. This is one of the major features that the RocksDB team developed and released this year. So here's the API, and my talk is mostly for these three, not the API, options. And my talk is mostly focusing on these three options on what is this, how to use that, and why we have that. So first of all, the tiered storage, in general, in LSM tree, the high-level data tends to be hotter, and the low-level tends to be colder. Why? Because data is in LSM tree, data is compacted from high level to low level, and which means the high level tends to have a newer data, and in most of cases, that newer data is hotter. And the read also starts from the high level to the low level. The RocksDB queries start level by level, and once it's find the data, it won't go lower. Another thing is compaction is also much more likely to happen in the high level. So all this reason makes the LSM tree kind of like the median, the storage median that the lower level tends to be cold. So because of the nature of that we introduce a option called last level temperature that the user could set. So typically user set it to cold, and in this case we RocksDB basically only bypass that setting to the RocksDB file system API. And to use the feature, user also has to write your own file system that to take the hints from the RocksDB and place the SS table in its corresponding tier. And here's also in the presentation there's a link for that, and how to inherit the class from the file system, RocksDB file system API. So one of the challenge for that, that approach works pretty well for level majority of the use case, but it may or may not work for universal compaction, because universal has a major compaction which basically compact everything to the last level or to the code tier, includes the recent write data and older data. Level compaction could also potentially have this problem if the new write data is in no overlap with any existing data, and it's likely to travel moved down to the level much faster. also because if the data set is highly skewed. So to overcome this issue, the second enhancement we introduced is time-aware tiered storage, which basically able to split the output to hot tier and cold tier in the last level compaction. A little bit about the, before that, how to use the feature is basically the second API that user can set, say, I want the last 3 days or 7 days data be guaranteed in the hot tier, and the other data could be pushed to the cold tier. A little bit about the implementation, just to help the user understand how the feature works and how to use the feature. So on the high level, there's 2 major components for this feature. One is called the time tracking feature. The other is the compaction that's able to split out the data. So the time tracking feature, what it does is it's periodically sampling the sequence number to the time information periodically. And the accuracy is based on the user setting. So as we can see, because it's a sampling, so it's not the exact time, but it's an estimation. The accuracy is depends on the user setting. For example, if it's 3 days, then we sample the data roughly about 1 hour. So the accuracy is also around that range. Once we have that information during the flush, the information is actually attached with each SSD. And there's a very small sequence time mapping attached in the SSD property. User will also be able to kind of look into that. Our SSD dump and other tools are able to pass and display this information. On the other hand, all this information is also kind of self-contained for each SSD. During the compaction, it will basically, the tier compaction, basically it will collect all this time information and find out the sequence number to split the hot and the cold data. Actually, it's basically newer and older data. And the compaction is able to, a tiered compaction basically able to, put the hot data in the hot tier and the cold data in the cold tier. There's a lot of implementation details, and I have a link to our blogs, which explains more detail about things about how we do the samplings and how we do the migration, the existing use cases that, if existing use cases don't have the timestamp information. Also, during the migration, it potentially could move the data from actually lower level to high level, which is never did before in RocksDB. And there's also some note, like snapshot of the data always put into the hot tier, because I think it's typically safe to assume most user snapshot data is hot. In that case, also means the tombstone will never be pushed to the last level, because if it's not a snapshot to protect the tombstone, it will always be kind of delete the physical data in the last level. But anyway, there's much more details in the log. The feature is still actively being developed. All the feature I just described is available and usable in the latest release. But the new features and the new metrics we are still adding. For example, the time-aware tier is only focusing on the time-aware policy. That's the latest time listed, assuming the latest data is the hot data. But the new policies may add, for example, based on the actual customer's usage of the access pattern. Yeah, and any contributions or any PRs or suggestions are welcomed. Thanks.
Hi, my name is Anand Anantabotla. I work on RocksDB here at Meta. And I'm going to be talking about the parallel Iterator IO feature that we recently introduced in RocksDB, along with my colleague Akanksha Mahajan, who did bulk of the implementation, but she couldn't be here today. So a little bit of background and context. The Iterator is basically a RocksDB API to allow an application to scan its database from a start key to an end key. Sometimes there is an upper bound on the end key, but other times it's an open-ended scan and an application can terminate it at any point. So RocksDB is LSM based, so a typical database has multiple levels. It has a few L0 files and a mem table, and an iterator under the covers. It maintains a child iterator for each level, an L0 file, and mem table. And the keys from these child iterators are merged into a single sorted stream. So the iterator uses the block cache as well to try to avoid going to the disk too often. So the typical pattern, IO pattern for an iterator is disk reads interspersed with block cache reads. So this is like an overview of how what we call a forward scan works. There's a variant which scans backward, but that's not applicable to this feature. So what's the problem we are trying to solve here? The problem we want to solve is the overall scan latency. So scans generally tend to be bottlenecked on IO, and the longer the scan, the more IO it has to do, and the latencies all add up. So every time there's a block cache miss, the iterator has to read a block from disk, and that stalls the scan thread. RocksDB tries to improve the situation a little bit by reading ahead more data than necessary anytime it has to read, in the hope that we can save some future IOs. This helps, but it doesn't completely eliminate the stall issue. If you're running RocksDB on a distributed file system, the problem gets even worse because the latency of accessing storage over the network is higher. So what can we do about this? How can this parallel IO feature help? So a scan is basically two parts. The first part is a seek, which the seek is basically figuring out the physical offset of the start key, or the smallest key that is greater than equal to the start key in the different files and different levels. And as I mentioned earlier, each database has multiple levels, multiple L0 files. So there are a number of child iterators that need to be positioned for the seek. So one simple optimization that we did was break the seek up into two phases. And the first phase of the seek, basically at each level and each L0 file, we walk the indexes, figure out which data block contains the key we are looking for, and then schedules an asynchronous read if any data blocks are missing. The second phase then goes through all of those child iterators, waits for the reads to complete, and then finishes positioning the iterators. So this allows us to exploit some I/O parallelism here by resolving these block cache misses in parallel. On Linux, we use the IO Uring API for doing the asynchronous reads, but this is extensible enough that different file systems, non-POSIX file systems, can provide their own specific implementation. The other component of a scan, and usually the most time-consuming part, is actually iterating through the key range through multiple next calls. So we also made an optimization here to try to speed up the scan. So what we do is we use multiple read-ahead buffers, and we asynchronously prefetch data into those buffers while the iterator thread is doing its scan and processing through the keys in memory. So we try to avoid stalling the main iterator thread as much as possible. And this asynchronous prefetch also allows us to exploit some parallelism here by prefetching simultaneously in multiple levels. So I can illustrate this through an example. So in this example, we have two SSD files in two levels. There are iterators for both the files. We have two prefetch buffers covering different ranges of the file. Once the upper iterator, once it crosses one of the file ranges, we recycle the buffer and immediately start an asynchronous read on it. Likewise, as the iteration proceeds and the next stable iterator crosses the file range in a buffer, we recycle it and start another async read. So there's some potential parallelism here. And eventually those reads complete, and then by the time these iterators reach that portion of the file, the data is available. So these are results from some benchmarks that we ran using this feature. We used DBbench to run these benchmarks, and it was run on a distributed file system that we use here at Meta, but externally known as Tectonic. And we saw like anywhere in the range of 20 to 35% improvement depending on the scan range and how many keys we are scanning. Yeah, so, and the first data point with 0 on the x-axis is basically just measuring the seek latency. It doesn't actually do any scan. And as expected, as the scan range increases, the gap also increases. And the parallel iterator scan tends to perform better. Sorry? Yeah, y-axis is the latency in microseconds. No, it's the average latency. But yeah, this we have seen in our benchmarks and other data that it also helps with the P99 latencies as well. So yeah, there is a blog post on rocksdb.org about this feature if you're interested. I had added a link, but I think there is somehow it's missing here.
Okay, hi everyone. My name is Changyu. I'm a software engineer on the RocksDB team. I'm going to talk about one of the things I've been doing for the past year. It's about improving range deletion performance. That means improving read and scanning performance when you use delete range APIs. So this is the last lightning talk, so please bear with me. I'm going to give an overview on how range deletion works in RocksDB, the write path, read path, and iterative code path. And then I'm going to show some benchmark results. So the delete range API, as you can see on the right of the slide, is basically introduced to mainly replace this iterate and scan delete pattern. So instead of creating iterator, go through from the start key to the end key, you can just issue a delete range blindly. It has several advantages as being a native API. It's simple, it's fast. You don't have to create the iterator, which is pretty slow. It's also atomic and works well with crash recovery. Now, how does it work? First is the write path, which is pretty similar to the put operation or delete operation. The write request is persisted in the write-ahead log. It's inserted into a mem table and then subsequently flushed and compacted down the LSM tree. One major difference here is that there is a separate mem table for range tombstones, which is a marker for range deletion inside RocksDB. The reason we have a separate mem table is that we want to enable efficient read querying, and we don't have a good way to put the point data and the range data together. So this is the read path for point lookup, so basically a get operation. The way roughly how get works in RocksDB is that we go through each level of the LSM tree until we found the point key or range tombstone that covers the point key. So the point key lookup is pretty efficient. In mem table, it's a lookup in the skip list, so it's log time. In each LSM level, it's a binary search on the correct file that contains the data, a binary search to find the correct data block, and then a binary search to within the data block. So we want the range tombstone search to be as efficient. However, since we don't restrict on the range that can be deleted through the delete range API, it's possible for user to issue overlapping ranges through delete range APIs. You can see on the top right of the screen here, let's say we have a mem table. We have these 3 delete range that are issued by the user that are overlapping. Imagine we sort these range tombstones by start key. You get A, C, and G. And if a user wants to query, let's say, key E, we would return C to D, but that doesn't cover the key E. It's the same story if we sort them by end keys. So we have this process that basically convert the range tombstones issued by the user into non-overlapping ranges. We call these fragmented tombstones. That enables efficient binary search. So the first optimization we've done here is to cache the fragmented tombstone result. So meaning each delete range operation will invalidate the cache, and the cache is reconstructed upon the next read operation. The iterator story is more complicated and more interesting. I think Anand described a little bit about how iterator works in RocksDB. So essentially, we have a merging iterator that combines the sorted key streams from different levels of the LSM tree into a single min heap. So this is very similar to the merge step of a merge sort. Now with range tombstones, each level also has a sorted stream of the fragmented non-overlapping range tombstones. So we advance the point iterators and the range tombstone iterators together. So for each point key that we get out of the main heap, we also check whether it's covered by a range tombstone, whether it's visible to the user. So this can be inefficient in a scenario where, imagine you have a large range tombstone that covers a lot of keys. We still have to go over each key and check if it's deleted by a range tombstone. So the optimization here we've made is based on the assumption that, or the observation that if you have a range tombstone at a higher level, let's say in this case a mem table, we know that it covers all the keys in lower levels. So instead of iterating through all the keys in L0 and L1, we can just jump till the end of the range tombstone. Now, we can walk through an example here. Let's say this is our state-of-the-art assembly tree. So all the iterators now will go through the same main heap. Let's say we do a seek on key A here. The position of each iterator is underscored. So the first key that will be returned by the iterator would be key A from the mem table. Now, let's say the user does a next operation. The next key that come out from the main heap would be the start key of a range tombstone. So in this case, we know this range tombstone is from the mem table. So all the keys that are from lower levels in the LSM tree are covered by this range tombstone. So what we can do is to do a seek operation on L0 and L1 here. So you can see the iterator position in L0 is advanced to H. And the same seek will result in the range tombstone from L0, which is from E to K here. We can apply the same story, basically seeking letter K into L1. If there are more lower levels, we'll do the same. So with this cascading seek optimizations, we don't have to iterate through the keys B and C here. We'll just get H as the next key. Here are some benchmark results. The benchmark performance is going to vary depending on how you delete your keys, depending on your workload, and how large is the range you delete your keys. So in this setup, we have 50 million keys, 10K tombstone patches, meaning 10 ranges we've deleted. They are deleted either through point deletions or range deletion. And the numbers here are the throughput from seek while writing dbbench. So we are doing iterator scanning while issuing write and delete range operations. So the optimization was introduced in version 7.7. In this benchmark, we see 30 to 60% in iterator throughput improvement. Some acknowledgement here. First is from Pebble, which is the storage engine under CockroachDB. I think they are the first one that implemented this cascading seek optimization. I want to thank Andrew from RocksDB team to reviewing all my code. And I want to thank an external GitHub contributor who implemented a potential mem table format that does not need fragmentation, that allows direct search of range tombstones. So that's everything. Thanks, everyone.
All right, cool. That actually ends the portion of our meetup that is talks. So we actually have dinner and social hour now until 8 o'clock. So a couple of logistics before we go into that session. So first of all, it is a hard stop at 8, unfortunately. So I hate to do this, but I'll have to kick people out at 8 because that's when security is going to be here. And then actually a few not so fun reminders, but this is really important. Number one is that this is a no smoking campus, and so some people were smoking and vaping in the courtyard out there. That is not allowed. And also, you do need an escort that is required to escort you around if you actually do, don't explore the building, but if you walk around, you need somebody with you. So if they actually catch people walking around without escorts, you will be asked to leave. Sorry about that, but there is some pretty strict security here. So because of that, I do have a humble ask for the actual dinner portion. We're going to keep people in this room, so we're not going to have people in the mini kitchen. We're not going to. You can maybe go back. You can go back there and get some food, but please don't wander around. You can go ahead and use obviously the bathroom and then just come back. So so yeah, that is the not so fun part of the talk. But please, like, if you guys can just bear with us, you know, this is pretty important. The other quick announcement I have is for anybody, for Uber and Lyft, in case you didn't read the meetup, they're not allowed to actually come to this portion of the campus and pick you up. So you will have to walk over to building 41 or 58. So please make a mental note. That is in the meetup announcement if you do want to be picked up by Uber or Lyft. So that's just a hard and fast rule. Like, we won't be able to be flexible on that. So other than that, like, again, please don't wander around. And then we have pizza and some food in the back. And please enjoy yourself. Please get to know each other. And thank you so much for coming. I hope the talks were useful to you guys. Again, a quick reminder, there will be a survey that goes out after this. So please fill in the survey. Tell us how we can improve. We're always looking for feedback. And thank you. I know it's, you know, investing your afternoon here is a commitment of time. So we just really wanted to thank you, everyone, for coming out. Yeah. Thank you.